Sener is a world leader in solar thermal power that counts on plants being built and several projects being developed, as well as remarkable initiatives in Spain and internationally. Sener is a development investment company, expert in construction, a specialist in turnkey projects, and an expert in technological developments. Sener's capacity for anticipation in this field, as well as its technological development programs, have always been directed at solving the problems to be expected in these thermal solar plants. In recent years, thermosolar technology has become increasingly important as a large-scale electricity generator. Out of all its variants, the most common is based on the use of parabolic trough collectors, where thermal oil is heated up to around 400 degrees centigrade by solar radiation. The solar field of a 50 megawatts plant with a thermal storage capacity equivalent to 7 hours is made up of 93 kilometers of collectors, with around 560,000 square meters of high reflectivity mirror surface. The solar field represents 40 to 45% of the cost of the plant. Given the technical and economical relevance of the collectors making up the solar field, Sener decided to undertake developing a new collector to improve the technical economical performance of the existing collectors. The objective consisted of reducing the energy uptake unit cost. With the new Sener trough collector, we have managed to reduce the assembly time by 50% and the structure weight by 10%. A collector's function is to concentrate solar radiation using a parabola made up of mirrors. The parabola concentrates the radiation that reaches it in a collector tube that transfers it to the oil flow that circulates inside it. The functional unit is the solar collector assembly, or SCA, made up of 12 12-meter-long collectors. The main requirements established for the new collector were the following: high efficiency, high durability and reliability, lower manufacturing, assembly and maintenance costs. The collector dimensions were established as 12 meters in length and 5.77 meters in aperture. A structure concept made up by the following elements was chosen: a central body called torque tube, some cantilever arms to connect the mirrors to the torque tube, and some collector tube supports to connect the tube the oil flows through to the torque tube. All the elements are made out of carbon steel given its good cost-strength ratio. This design minimizes the amount of parts and connection elements per collector and increases the torsional stiffness as regards existing space latticework designs, obtaining minimum amount of elements, high repeatability in element manufacturing, high accuracy of manufactured elements. The torque tube is the collector's strong nucleus. It consists of a tube made out of low-thickness helical sheet to which some plates are welded to fasten both the cantilever arms and supports of the tubes. The joints have been designed to obtain minimum deflections of the key elements, mirrors and tubes. After manufacturing, the torque tube is hot dip galvanized. The collector tube supports and cantilever arms are the most important innovation in the Sener trough collector. They have been designed with sheet stamping technologies from the automotive industry, as these parts requirements are quite similar to the ones used in this industrial sector. High accuracy and high repeatability are obtained with this technology at low cost. Pre-galvanized sheet metal is used for manufacturing them. The design of these parts has also allowed for considerably reducing their weight, making them easier to handle. Furthermore, these parts allow for very compact packing, which makes transporting them cheaper. They have been structurally analyzed, taking wind tunnel tests and fluid dynamic simulations as a starting point. For calculation, the use of conventional structural analysis software has been combined with the use of automotive and aeronautics mechanical calculation and design tools to obtain optimum design. Two variants of the structure have been defined that allow for installing in each area of the field the variant with the strength better fitted to the wind loads it is going to suffer in the specific point where the collector is positioned. The existence of two variants also allows for installing solar fields in areas with very different wind speeds, from 120 km an hour to 160 km an hour, without changing the elements. Suitable bending and torsional stiffnesses are also obtained. The latter key to the device's performance is 3 times higher than the collectors currently on the market and allows for the parabola to turn homogeneously and evenly throughout all its length. The collector is assembled in a temporary assembly building installed in the construction plant. The tools and jigs necessary for a quick and accurate assembly and for checking the collector's geometric accuracy and correct balance are in this building. The collector components arrive in this assembly building and the checked collector modules leave it, which are taken to the solar field for final assembly on the pillars. The assembly and checking process is carried out in 3 workstations. The first is the structural assembly station where the collector's structural elements are assembled. They start by positioning the torque tube in the assembly jig. The cantilever arms are then placed on the positions defined by the jig in the mirror anchoring points, and the cantilever arms are fastened to the torque tube. Finally, the collector tube supports are placed on the positions defined by the jig and fastened to the torque tube. In this way, the collector module structure is assembled, guaranteeing a correct relative position between the interface points that define the collector's geometry, collector rotation axis, mirror anchoring points, and collector tube position. The quality of the collector depends on this main workstation. The collector is then turned 180 degrees and positioned in the second station, where the geometric check is carried out. The collector's structure is rested on the ends of the torque tube, and with a measuring station, the position of the mirror anchoring points and collector tube fastening points are measured. The values measured are automatically processed, and the evaluation of the geometric check carried out is obtained immediately before continuing the assembly process. Acceptant percentages are around 100%. After carrying out the geometric check, the collector's structure is moved to the third station, where the mirrors are assembled. Each mirror is directly fastened to the structure's cantilever arms. Finally, the collector's balance is checked. This operation is carried out turning the collector module 90 degrees and measuring the unbalanced torque. As it has a high torsional stiffness, counterweighting hardly any collectors is necessary during the construction of a plant. Before placing the collectors on the pylons, all the bushings of each of the 300-meter rows have been aligned with precision topographical equipment. Pylon design allows for absorbing the positioning tolerances of the bolts and obtaining the necessary accuracy in bushing position. When all the bushings have been aligned, the collectors are positioned and fastened. In a last phase, all the collectors are aligned in torsion, and the collector tube's sensors and electronics are installed. The actuation system is based on 2 cylinders and hydraulic unit, capable of turning the 150 meters of collectors. This movement is controlled with a band-shaped magnetic encoder that records the collector position with an accuracy of 0.02 of a degree. The electronic controls this movement and allows for positioning the collector in the solar radiation direction with a state-of-the-art mathematic algorithm. This solution allows for preventing problems with shades and dirt, typical in solar sensor based on photovoltaic plates, also preventing the calibration processes required in the latter. Collector validation has been an incremental process that has taken 4 years. In a first phase, a prototype of SCE was assembled in the Almeria solar platform. A prototype loop was then assembled in the Andasol 1 thermosolar power plant. Finally, the good results obtained have led to the construction of the first two plants with this technology, Extrasol 1 and Extrasol 2, where a total of around 186 kilometers of Sener trough collectors are being installed. Performance measuring has been carried out using a portable test platform called POTS, capable of moving the rated oil flow around the tested loop and using a large fan to dissipate the heat produced by the collector. The loop's performance is calculated from the accurate measurement of temperature in the input and output and the flow and data of the meteorological station's incident radiation. Sener is working on a new larger size model of the Sener trough collector. Each collector will have an aperture surface almost 20% bigger than the current design, which will allow for reducing the amount of collectors necessary for capturing the same amount of energy. Although the individual cost of each collector is higher given its bigger size, the reduction in the total amount of collectors will reduce the overall cost of the solar field. Sener has developed the Sener trough collector with 100% owned technology, improving performances and considerably reducing its cost as regards existing collectors. This has only been possible thanks to Sener's multidisciplinary character, as its knowledge areas cover all the disciplines involved in the design.